All right. So we are doing section 1, fact 3 now. We talked about the definitions of functions. Now we're going to go into the graphs of functions. We're going to be able to find domains or ranges of functions and apply the vertical line test. We have already done that, have we not? Bam, done. Done. But we're going to do it again, just for Department of Redundancy, Department Policy. So that's 1. 2, determine intervals on which functions are increasing, decreasing, or constant. 3, determine relative maximum and minimum values of functions. B, identify and graph step functions and other piecewise defined functions. I don't think we're going to have time for this. It's not terribly important right now, so we're going to put a line through that, but reserve the right to rescind that line if time allows for it. Lastly, identify odd and even functions. So, let's begin. First of all, let's go with reviewing section 2. What is the domain of this function? Badly drawn graph. There's Logan. That's okay. That's okay. I'll update. I will update. Oh, no, I didn't mark graphs. How cool is that? I'm having trouble keeping track of who has a plan. No, you did not. Now that I realize that.
Yeah, we just got a plan.
Just throw Mr. Folkert under the bus. It's all good. So what we're doing, Logan, is we're trying to figure out what the domain of this function is. Who's got some input? Somebody other than Henry. Is it all the real numbers? No, it's a part of the real numbers, right? What part? -1. Okay. -1 is part of this domain. Okay. I'm going to use interval notation here. So you said -1 is the lowest value, right? Do I put a square bracket around the left-hand side or a curved parenthesis around the right hand? Why? Because it's equal to, right? That's a filled-in dot there, so it is a square bracket. Okay? And then what do I put in interval notation after the -1? No, you're thinking inequality notation. I'm going to put a comma here. Comma, right? And then what do I put? 4. But how do I show it's less than but not equal to? That's right, a parenthesis. And because of set notation, I got with my other mustache bracket there. That's going to be what we call that, a mustache bracket, because mustaches are coming back in, right? November's coming in a couple months. You'll see some mustaches rocking around here. So that's my domain. How about the range? What is the range of this function? I asked quietly to myself. I didn't number this all the way, did I? What should I have done to completely number this? To scale my axes properly. And I should have gone negative values on my y-axis, should I not have? Let's see. How far down should I go on my y-axis? -5, I heard somebody say very quietly, so that, there you go. Okay, -1, -2, -3, -4, -5. Okay, -5, I like that. Negative 5. I wrote it in red just to be confusing, but that's okay. So my range is defined as, shall I do the inequality on this one, just so that we get practice doing it both ways? Let's do that. Let's do that. So what is the bottom of my range? negative 5. What should I put? We're doing inequality, right? Less than or equal to. Greater than or equal to. What is greater than or equal to negative 5? Very good. I think some of you guys were in my morning section yesterday, and I did the range with an X. Did I do that? I think I did that to y'all. That's a no-no, right? Because my X was, I mean, it can be, but in that case, it was not the variable that I was using for my range. So let's erase that and put the proper variable in there, which is Y. And then what? Oh, did I screw up again? It goes that way. Y is greater than or equal to negative 5. Or I could read that as negative 5 is less than or equal to Y. Right? I usually read these from left to right. So those of you who said less than, I'll give it to you. Those of you who said greater than, I'll give it to you too. Why? Because I'm assuming you meant negative 5 is less than Y, less than or equal to Y, or that you meant negative 5, or I'm sorry, Y is greater than or equal to negative 5. But typically, how do we read this sign? Well, because we do it left to right, right? We assume we're reading left to right. So we say negative 5 is less than or equal to Y. Okay? And then this one is simply a less than. Less than, ooh, is it less than 4? Let's look. That raises a question. Do I know it's less than or less than or equal to? We can't really tell, right? Well, what if I did this? What if I told you that f of x equals, let's see, what would that be? That would be x minus 2 quantity squared negative plus 4. What if I told you it was that? Plug 2 in for x, because it looks like the peak of this parabola is at x equals 2, right? So evaluate f of 2. So f of 2 is 4, right? So what should this be? Y is less than or equal to 4. And there I have my set. Because it's set notation, though, always put your set notation in mustache brackets, okay? So, we've answered A, which is my domain. We said, what's f of negative 1? Down here, we said definitely negative 1 comma 5, right? So f of negative 1 is negative 5, definitely. We weren't sure about f of 2 until I defined the function for y'all, right? Once we defined the function, then I could definitely say it was 4. But until then, we had to read the graph. Now, if I'm reading the graph, can I tell if it's 4 or getting really, really close to but not quite equaling 4? I can't tell, but I would suspend all that critical thinking, knowing that my graphing is not precise, and just say f of 2 equals 4. But then, once I define the range, we got our range right there. Okay, so now I want to look at example 2 on page 31. We're going to define the domain and range of f of x. F of x is defined as the square root of x minus 4. What does it mean? Is this a function, first of all? Ignore that. Look at that. Is it a function? Bailey gives me the thumbs up. Why is it a function? Thought square roots produce positive and negative values. So if there's no positive or negative sign, that's the first thing I'm looking at. The other thing is, I'm saying it's a function to y'all, right? Which means it can have only one value for y for every value of x. That's the definition of a function, okay? So that's what makes this like this. It looks janky because I didn't draw this with the pen, I drew it with the mouse. Really hard, but anyhow. Looking at the graph. Let's do this graphically first. Looking at the graph, what are my possible values for x? This is my x. This is my y. I really should put those down. What do you think, Sam? What are my possible values of x? Looking at the graph. X could be 3. It's hard to see because it's far away, right? But what is this point right here? 4, 0. Okay? So this point here is 4, 0. And x can be anything greater than or equal to that, right? So if I look at this graphically, I would say the domain is x is greater than or equal to 4. There we go. Okay? Looking at it here, algebraically, I know that x minus 4 has to be greater than or equal to 0, do I not? Why do I know that? Right? Because we're defining, and I don't think I covered this in the first section yesterday either. But until your glasses upside down, you have the same prescription in both eyes. Wow. Wow. Okay. Until told otherwise, we're always going to define our functions as having a domain in the reals, and the range is going to be in the reals. So it's going to take a real number and produce a real number. So I return to this question right here. Why do I know that that's true? Who's got some insight as to that? Remembering that we're practicing our academic language in mathematics. You want to try and give it a stab, Haley? Negative numbers are real numbers, but the square roots of negative numbers are not real numbers. You're on the right track. We just got to get our language precise, right? Good. Good. So if I take this expression that I know must be true, based on my assumption, then I can solve for x. And I say, oh, well then I know x is going to be greater than or equal to 4. And look, our algebraic method matches up with our practical method. How about the range? What would the range of this function be? Let's look at that graphically. Let's do this in green. What would be my range, looking at it graphically? H, you got something? Greater than or equal to 0. But doesn't it look like it's approaching horizontal status? Yeah. I mean, if I go all the way out here, right, that might only be like this tall. But should it get horizontal eventually? Never? Okay. Yeah, because you give me a number that's really huge for x, right? I take the square root of that x minus 4. I'm going to get another really huge number. Not as big as my x, but still big, right? I can always find something bigger than that, right? This will never stop increasing. That is important to recognize. Okay? There is no asymptote on this graph. Okay, so my range is going to be defined as, and let's do interval notation this time. What's my minimum value? Then 0 is my minimum value. Should I put a square bracket around the left-hand side of that or a parenthesis? Then you think a parenthesis. Can this equal 0? If I look at my graph, it's hard to tell, right, Ben? But this is a judgment call here. If I'm telling you to do it graphically, remember, this is a judgment call. Now, how do I, if I put a dot here, when I drew this, I made sure to put a dot there, then is it a judgment call? No. If I drew this and put a circle there, is it a judgment call? No. But I didn't do either, right? So then, it's a judgment call. But let's assume then that I put a dot there. Get the blue out there, get the blue out. All right, then, what kind of bracket? Bracket or parentheses? Bracket, because it can equal 0, right? Okay, and then what do I put? Zoe, what do I put after the 0? Thanks, Zoe. And then, welcome back, Lyndon. After the comma, what do I put? What do you think, Tyson? Infinity. And after the infinity, Logan Crawford, whose glasses are now right side up. What do I put after the infinity sign? Parenthesis or parenthesis? Parenthesis. Good. Be confident. All right. And then after that, Noah? Mustache bracket. Industry term, right? Technical term. Okay, excellent. We have given this. Now, why am I doing the parenthesis around the infinity and not a bracket? We're saying this goes up to infinity, right? Infinity is infinity. Why not put a square bracket? Is infinity a number? No. It's an idea, right? And that idea says, give me the biggest number you think of. Henry, give me the biggest number you can think of. 38 billion. 38 billion and 1. I can come up with something bigger. No matter what Henry chooses, I can come up with something bigger. So this will never be, when it's infinity, it will never be a square bracket around infinity. As it will never be less than or equal to infinity if I'm using that notation. That will be graded. I will ding on that. That is a very important idea that we need to have in Unit 11. Okay? No number can equal infinity. No variable can equal infinity, because infinity is not a number. Remember this. Okay, so we talked about this already. Now, let's talk about this real quick. A set of points in the Cartesian plane. What did we say the Cartesian plane was? What name have we given it all the way up until this year? Coordinate plane. Why do I call it the Cartesian plane? Is it because I like to sound fancy? Give the man his due. Who's the man? No, Rene Descartes. Rene Descartes. I think before, no, not I think before. I think, therefore I am that guy. He came up with this. We're giving the man his due, okay? So, set of points in the Cartesian plane is the graph of y as a function of x. Okay? Good morning. So, we talk about f of x, right? We talk about f of x. Oops. Oops, I want that in red. My graph is red. I talk about f of x, right? But I'm graphing it on the Cartesian plane, which is x coordinate and y coordinate, right? How do I do that? I don't see a y in this expression. If I said this was my expression, I don't see a y in there. How do I put it on the Cartesian plane? I set my function equal to y. Okay? Now, that's how I get it on the Cartesian plane, because I set it equal to y. Now, this definition says a set of points of the Cartesian plane is the graph of y as a function of f, if and only if. And this is the abbreviation for if and only if. It's if. No vertical line intersects the graph of the function at more than one point. What's our shortened definition? A function is a function on the Cartesian plane if it passes the vertical line test, okay? That's this in academic speak, okay? Now, here's where it gets tricky again. A function is increasing on an interval if for any, this is what for any is in math speak, an upside down capital A, for any x1 and x2 in the interval, if x1 is less than x2, that implies that f of x1 is less than f of x2. Do you need to know these definitions verbatim on a test or quiz in my class? No. That wasn't a statement, that was a hope, right, Haley? I was like, please don't make that testable. I don't need you to know this verbatim. I do need you to apply it. Okay? Because I'm going to ask you, is this function increasing or decreasing? I'm going to ask it to you, giving you a graph. I'm going to ask you, giving you function values. I'm going to ask you, is it increasing on this interval? And you're going to say, yeah, it is, or no, it isn't, based on this definition. So you don't need to know this, but you do need to know how to apply it. Does everybody understand the difference to that? Okay? Here, a function, f is decreasing if for any x1 and x2, not just a particular x1 or x2, but any x1 or x2 where x1 is less than x2, it implies that f of x1 is greater than f of x2. And that makes sense, right? If, I need another sheet of paper for this. If I have a graph, right? And I got x1 and x2. That function is decreasing if f of x1 is greater than f of x2. It's easy to figure out if a function is decreasing on a graph, right? What's harder to do is understand this. And sometimes books are written this way, so you need to be able to apply the symbolism that we use in math, okay? Now, a function is constant if, when for any x1 and x2 in the interval, if x1 is less than x2, what's true? F of what? If x1 is less than x2, f of x1, f of x2. What operator should I put in the middle of that? If it's constant. Equals. Thank you. And actually, I don't even care about whether or not x1 is less than or x2. I don't care if it's greater than. It's for any x1 and x2 in the interval, that's true. And that is our condition. So function is constant on an interval if for any x1 and x2 in the interval, f of x1 equals f of x2. Excellent. Now, relative maximum and minimum. I think this is easier if we look at a graph. If I have a graph that does that, there are all sorts of relative maximums and minimums in that graph. Where are they? Where are the relative maximums? You will also hear this referred to as a local maximum. Maybe that term helps you a little bit more. Where do you think the local maximums are? Who's got a clue or an idea? Clue's a bad term. Who's got an idea or an intuition as to what that might be? So takers? Okay. I asked a question. If I zoomed in where I could only see that, what's the maximum of that function? At the high point, right? At the peak. Okay? This is a local picture of the whole thing. You get what I mean by local now? We also call it relative because relative to the points around it, it's at a maximum there. Feel me? Okay. So, what's a relative minimum? The maximums are the peaks. The relative minimums are the valleys. Like that song. Hey. You ever wonder what it's like for Bob Dylan to sing that song? You just heard it. So. Who gets Bob Dylan jokes? Who gets Bob Dylan singing jokes? Of course, Wyatt gets the Bob Dylan singing jokes. Connor, to a lesser extent. Nobody else? Caleb gets it. Logan gets it. Mason, you don't get the Bob Dylan singing jokes? Oh my goodness. I'm going to have to play Bob Dylan songs in here. Then everybody's going to get it. All right. So, translation. Look for the peaks and valleys, right? Here's the academic definition. Look for the peaks and valleys. Okay. Now, okay, let's do a test here. How many relative maximums do you see in this picture? And minimums? That's a good question. Is this or this a relative maximum or minimum? Here is where this becomes important. So the end of the graph was this guy, the x. There was an x1. So on the far right of the graph, right? So if this is x, is there an x1? Looking back at this, x1 means there's something less than it, right? Is there an x1 over here? Is there an x that's lower in value than this x? Yes. Is there an x2? No. So can I call it a relative maximum? No. Same with this one right here, right? There's an x2. There's an x value that's greater than this x. But is there an x1 with a value lower than it? So I can't call it a relative minimum either. Okay? Okay, good. Good, good, and good. So now, I don't want to go into piecewise functions. But I do want to go into even and odd functions. We're just about done with this lesson. Can you believe that? Can you believe it? Can you believe it? Okay. So we got until 9:50. We might even get some work time here. But this is the hardest part, okay? I do need you to know these definitions. These definitions, you do need the academic definition down because we're going to apply this logical test over and over again in this section. So, even functions follow this property. It's not a wordy function, or not a wordy definition rather, but I need you to know it. I need you to know it like back of your hand. If f of x equals f of negative x for all values of x, then it's an even function. Then it's an even function. So in other words, for example, when x equals 2 or it equals negative 2, they produce the same value for the function. So when I evaluate f of 2 and f of negative 2, they're equal. But I didn't put this on the in other words, what if f of 2 and f of negative 2 have the same value, but f of 1 and f of negative 1 do not? I choose this variable x to mean all values of x. Okay? So it's not just, I'm not just plugging in a number. This is what my students in last year's class did a lot. They would plug a number in, and then they plug its opposite in there. And if they got the same value, they said, yeah, it's an even function. But you can't do that because what might be true for 2 and negative 2 might not be true for 1 and negative 1. You've got to use the variables. Now, what do I mean? Let's take f of x equals x squared. Is it an even function? Is it even? If Henry says yes, but if you put yes on your test, I will make it leave. Because what do you need to do? You need to justify it. So we're going to apply our logical test. So in other words, is f of x equal to f of negative x? How do I do that? Well, f of x is x squared. Does that equal negative x squared? Why did I put parentheses around negative x? Is this the same as that? Why? To quote my son, Ken Dospra, right? But that's not academic language, so let's use some academic language. I'm going to love this year. This year is going to be so fun. And next year is going to be just as fun because I'm going to do the same thing to your brother. And then 2 years after that, I'm going to do the same thing to your sister. So, so why? What am I squaring here? Just the x. That's Venn diagram, right? Exponent comes before multiplication. This is the same as saying negative 1 times x squared, right? If I wrote it like that, it would be easy, right? Because I know multiplication comes before the exponent. But I didn't write it like that. I wrote it like this. And it's not always apparent. Be very explicit in your writing communication. Once you get into a professional community and you understand what's implied, then you can start peppering that implication in. But until then, be explicit, okay? What does explicit mean? Clear, concise, say everything you say with saying it. Don't say as few things as you can without saying it, right? Okay, so if I square negative x, I'm squaring the negative and I'm squaring the x. Well, negative times negative is a positive, right? So this is x squared, and that equals x squared. That's a true statement. Okay? So this is an even function. Okay. Odd functions follow this property. F of x equals negative f of negative x. So in other words, when x equals 2 or negative 2, they produce opposite values. So f of 2 might equal 3. And if it's an odd function, f of negative 2 would produce negative 3. So, let's do an example of this. Is x cubed is f of x equals x cubed an odd function. In other words, does is f of x equals to negative f of negative x. I want to see, when you get these problems, I want to see these steps written out. I want to see the logical test. Apply. So now I plug and chug, right? Oh, I put x squared. I meant to put, I think I said it, but I didn't write it. I meant to write x cubed. Is x cubed an even or an odd function? So now let's apply it. So if f of x is x cubed, well, this is x cubed. But now I'm doing negative f of negative x. So I'm doing negative x cubed. Unpack that. Did I do that correctly? Did I put negative x into that function correctly? What do you think, Josh? Think so. Okay. And you think correctly. So I put negative x into this function, I get the quantity negative x all cubed, right? But I'm taking the opposite of it, so I put the opposite sign in front of it. Now, what is negative x quantity cubed equal to? Not the negative sign in front, just the stuff inside the parentheses, all cubed. What do I get? Yes. So this is negative x cubed. I can move that in, right? Because this equals negative, I'm going to put this in there, negative 1 cubed times x cubed. Negative 1 cubed is negative 1, right? Negative 1 times negative 1 is 1, times negative 1 is negative 1. That's where that comes in. And then the x cubed is x cubed. So I can't forget that guy, right? So that guy gets brought down, and then, to quote Ms. Driscoll, boom, 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 boom. And that equals x cubed. And does x cubed equal x cubed? Do not plug a number in and test it with the number. Why? Because a specific number is not universal. This is universal. This works for all values of x. 3 is not all numbers. 17 is not all numbers. You could try 30 numbers, and I'm not going to be happy, even though you did a ton more work than everybody else. Because 17 numbers does not encapsulate all the real numbers, does it not? How long would you have to work to show me that this works in every case of the real numbers by using every single real number? It hasn't been done yet. Has not been done yet. Now, oh yeah. So, I want you to look at these functions. The function on the left is an even function. What can you say about that even function? If I put a mirror here, if I put a mirror right down here, facing the positive x-axis, it will look just like this, right? So we say that even functions are reflections about the y-axis. So they look the same on either side of the y-axis. That's an even function graphically. An odd function graphically reflects about the origin. So if you've got a value up here, it's the same down here. And my origin is not good, so this one technically would not be an odd function, but you get the general gist of how it looks. It looks the same on the right-hand side as it does on the left-hand side, except in the other quadrant, right? So, even and odd. We say this one reflects around the y-axis. We say this one reflects about the origin. Okay? Do this one on your own. I want to know if this is an even function, an odd function, or neither. So, I would suggest doing even first, odd second, and neither. So if it's not if it's an even function, can it be an odd function? Can it reflect about the y-axis and reflect about the origin at the same time? I hear different responses. So if this were to reflect about the y-axis, that means it's here and here at the same time. If it also reflected about the origin, if it's here, it would also be down there. So it's here and here at the same time. Does that pass the vertical line test? So can it be even or odd at the same time? No. Okay, so if you do this first test and you find it's even, you're done, right? If it's not even, then what do you have to do? Apply the odd test. What if it's not odd? Is that possible for a function to be neither even or odd? Absolutely it is. Okay. So if you haven't done it already in your notes, do it now. One lucky customer is going to get called up. I'm going to change this function. I don't want to work a trig function right now. What am I going to work? Let's see. That's what we're supposed to do. Let's save this or something right now. here's the 13. Yeah, rubber sole shoes is hard. I have rubber sole shoes. Okay. So that 3 is throwing some people for a loop, is it not? Who doesn't know what to do with the 3? Okay, let's get you started here. So, is f of x equal to f of negative x? What do I do with f of x? Well, f of x, it's defined for me here, right? So f of x is just, oops, it's x squared plus 3. But what is f of negative x? Well, remember, how do I evaluate a function? If I said this was f of 2, I would plug in 2 where? Wherever I see an x, right? Well, this is negative x. Where do I plug in the negative x? Wherever I see an x, right? So this is going to be negative x squared plus 3. Yes? Okay. So then, this becomes, go ahead, Ben. Positive what? Positive x squared, right. Again, we're being precise, right? Positive x squared plus 3. And positive x squared plus 3 over here. X squared plus 3 equal x squared plus 3 every time, right? So I'm done, right? This is even. All right. I gave you a hot garbage here. Gave you a hot mess here. Now, let's figure out if this function is even, odd, or neither. X equal to f of negative x. By your test. So plug in x into f of x and you get the same thing, right? Keep doing that. That's f of x, right? What is negative x? Yes, sir. Ah, thank you. Thank you. Attention to detail, Caleb's killing it. Killing it. So, if we evaluate that. Is this my even test or my odd test? even test, right? The only difference if I applied my odd test would be putting that right there. That would be my odd test, right? Well, we're not doing that first. We're doing this first. I'm going to show you a shortcut to the odd test. Now, this says this. This can simplify. What is negative x quantity cubed? Negative x cubed, right? How about this? I got negative x squared. That's just x squared, right? Do I keep this guy? So that's minus 6x squared. Ooh, I can tell already. We got a discrepancy, right? Well, let's finish this because it's going to help us. You do believe me, don't you? Plus and the minus, what's that going to be? Minus x, minus 1. Okay. So it's not an even function. Not even. Okay. Not even. Is it odd though? Yes, sir.
If it was 6x squared on the bottom, wouldn't it be 6x squared and then multiplying to negative?
Remember your order of operations, my friend. If I squared the negative x, that's going to be positive x squared. And I'm subtracting it. Good question, though. All right. Now, remember, I said the only difference between an even and odd function test is that guy, right? Well, I've already done this, right? So I'm going to do this in blue. Let's take this whole thing and put a minus sign in front of it. And this is Mrs. Driscoll on steroids, right? Boom, 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 boom. Is it odd? This guy right here, right? And this guy right here. That's not odd. So this is neither. I am posting the problem set, or the practice set. I am posting the practice set to my website. I'm going to post this video to the website as well. We are done with this section. The problem set for this and for section 1.2 due Tuesday, quiz time on Tuesday. Capiche? Good work, everyone.